A bombshell just dropped on the astronomical community, but it wasn't from space. While the West's most powerful telescopes were blind, Chinese observatories released crystal-clear images of the interstellar comet 3I-ATLAS. This isn't just about a new comet, it's about a seismic shift in who controls our view of the cosmos. This sudden pivot in the observational balance is stirring more than scientific curiosity. It may signal a new era in how we monitor these alien visitors. Let's explore this together.
Strange composition.
So, what makes this visitor from another star so bizarre? Interstellar objects are messengers from distant star systems, and 3I-ATLAS is only the third one we've ever confirmed. Unlike its predecessors, Oumuamua and 2I Borisov, this comet is giving us an unprecedented look at the chemistry of another solar system. Early observations from teams led by astronomers like Quanji Ye, using instruments like the James Webb Space Telescope's NIRSPEC, have revealed an unusual chemical fingerprint. The cloud of gas and dust surrounding it, called a coma, is incredibly rich in carbon dioxide, with some studies suggesting the CO2 to water ratio is more than 10 times higher than that of typical comets from our own solar system's Oort cloud, like comet Hale-Bopp. This suggests it formed in a very different and likely much colder environment, possibly in the outer reaches of a red dwarf star system, with a nucleus estimated to be between 2 and 5 kilometers in diameter and a hyperbolic trajectory with an eccentricity greater than 3. It's a pristine sample of the building blocks from a completely alien planetary system, delivered right to our doorstep. Every piece of data is a clue to how planets and life might form elsewhere in the galaxy, which is why every single observation is so critical.
Telescopes go dark.
But what happens when our best eyes on the sky suddenly close right as this once-in-a-lifetime visitor is putting on its best show? This isn't a hypothetical fear, it's the reality that just unfolded. Major observatories like the Hubble Space Telescope, the JWST, and the European Southern Observatory's Very Large Telescope are the workhorses of modern astronomy. They provided the critical data that shaped our initial understanding of 3I-ATLAS. But these are incredibly complex machines. In mid-2024, Hubble had to switch to a single gyro mode, a necessary fix that nonetheless impacts its efficiency and scheduling flexibility. The VLT's 4 main telescopes periodically go offline for the recoding of their massive 8.2-meter primary mirrors, a delicate process that can take a telescope out of commission for weeks at a time. Even the JWST has faced challenges with its instruments. The transcript suggests several of these key Western telescopes went offline just as the comet's activity was evolving, creating a critical data gap. This isn't just bad luck, it exposes a systemic vulnerability in a highly centralized system, a single point of failure that can blind us at the worst possible moment.
China steps in.
But the sky is never truly silent. Someone else was listening. Into this observational vacuum, China's astronomical community stepped forward, leveraging their growing network of advanced facilities, such as the 2.16-meter telescope at Xinglong Station, part of the National Astronomical Observatories of China. They released sharp, high-resolution images of 3I-ATLAS. These aren't just blurry snapshots, they are deep-field images that capture the comet's evolving structure with stunning clarity. Established in 2001, the NAOC has rapidly developed world-class capabilities, driven by a national strategy to become a leader in astrophysics. Scientists like Jing Li and her colleagues are at the forefront of this effort, utilizing these modern facilities to monitor transient astronomical events. By capturing fresh frames of the comet's coma when other major facilities were dark, Chinese astronomers didn't just fill a gap, they seized a moment of scientific leadership. The timing was impeccable, demonstrating that years of heavy investment outlined in their 5-year plans have paid off, positioning them to make critical contributions right when they matter most.
Data controls narrative.
Here's what really matters. In science, the person with the data writes the first draft of history. By capturing and publishing the first high-quality images of 3I-ATLAS during this critical window, Chinese teams will inevitably shape the scientific narrative. These initial observations become the reference points for all subsequent research. Think back to 1995, when Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b. Their data, showing a massive planet orbiting its star, in just over 4 days, created the hot Jupiter category and dominated exoplanet theories for years. Similarly, The Chinese images might be the first to identify key features in 3IATLAS, setting the agenda for the entire global community. Their interpretations, published rapidly on preprint servers like Arxiv, will gain significant mindshare before the formal peer review process is even complete. In a scientific ecosystem where reputation and early access are paramount, this gives Chinese teams a powerful boost, allowing them to take the lead on developing the first credible models of this alien object's behavior and origins.
Data sovereignty.
This isn't just about science, it's about control. For decades, Western astronomy has largely operated under a philosophy of open data, with archives like NASA's MAST providing public access. But that's not the only model. For example, data from the European Southern Observatory often has a one-year proprietary period for the observing team before it becomes public. As different nations become major players, the question of data access becomes more complex. The decision to release or withhold data can become a powerful tool of soft power. If China's new images and follow-up data are shared openly, it could foster a new era of global collaboration. However, if access is controlled through institutional channels, it could complicate independent verification and sideline researchers from other countries who lack the right connections. This situation brings up serious questions about scientific sovereignty and the norms of data sharing. Who owns data from the cosmos? How that question gets answered will determine whether the future of astronomy is more collaborative or more fragmented and competitive.
National prestige.
Let's be clear, observing the cosmos is about discovery, but it's also about power. Space science is deeply intertwined with national pride and global influence. China has long used its space program to showcase its technological prowess. The Chang'e 5 mission in 2020 returned 1,731 grams of lunar material to Earth, the first sample return in over 44 years, a massive prestige victory. Releasing key images of a rare interstellar wanderer like 3IATLAS, especially when others cannot, is an equivalent statement in deep space science. The media narrative practically writes itself. China steps up when others falter. This resonates far beyond academic circles, bolstering national prestige and justifying massive government budgets for science and technology, creating a self-reinforcing cycle of investment and achievement. It reframes the 21st century space race as a contest not just of exploration, but of knowledge generation, positioning China as a leader in a frontier domain previously dominated by the West.
Infrastructure fragility.
What does it say when the world's most powerful eyes can all blink at once? This episode serves as a stark reminder of the fragility of our global astronomy infrastructure. The catastrophic 2020 collapse of the 305-meter Arecibo Observatory is, honestly, a perfect example of how the loss of a single, unique facility can leave a massive gap in our scientific capabilities for years. For decades, the community has relied heavily on just a handful of flagship observatories. While these telescopes are incredibly powerful, this centralization creates a single point of failure. Funding cycles, maintenance, or technical issues can take multiple key instruments offline simultaneously. The 3IATLAS event really proves this model is unsustainable for time-sensitive science. It highlights an urgent need for a more diversified and distributed global network, something the upcoming Vera C. Rubin Observatory in Chile will help address with its continuous sky survey. Relying on a few titans is a risky bet when the universe doesn't wait for our schedules, and a single nation with agile facilities can now step in and dominate a major discovery.
Verification questions.
New data is thrilling, but it arrives with a critical question: can we trust it completely? The scientific process is built on verification, and integrating the Chinese data on 3IATLAS isn't simple. Are the new images calibrated in a way that is fully compatible with previous data? To answer that, the global community needs the raw FITS files and all associated calibration frames, the darks, biases, and flat fields required to remove instrument signatures. Without these, it's impossible to perform accurate photometry, the measurement of the comet's brightness, to see how its activity is changing over time. Furthermore, high-precision astrometry, or the exact measurement of the comet's position against background stars, referenced by the Gaia catalog, is crucial. This data is needed to refine 3IATLAS's hyperbolic orbit and search for tiny non-gravitational forces caused by outgassing. Full transparency, including sharing data reduction pipelines, is the only way for the results to be independently replicated and universally accepted by the scientific community.
What the images reveal.
So, what are the Chinese observatories actually seeing in these new frames? The released images are more than just pretty pictures. They are rich with scientific data that allow for precise physical modeling. Observers are pointing to subtle but significant details, like hints of new jets of gas and dust erupting from the comet's nucleus. These jets are crucial because they produce non-gravitational forces. They act like tiny rocket thrusters that can subtly alter the comet's path by hundreds of kilometers. Tracking these minute deviations, a specialty of astronomers like Marco Micheli, requires high-cadence astrometry from images like these. Furthermore, brightness gradients across the coma seem to be shifting, which could suggest that the outgassing is anisotropic, happening from specific active patches on the surface. By taking many images in quick succession, the Chinese teams can monitor rapid, transient events that might otherwise be missed. This morphological data provides the crucial visual context needed to interpret spectral data from other observatories, past and future, becoming the scaffold upon which a complete understanding of 3IATLAS will be built.
Global wake-up call.
Bottom line. This event is a shock to the system of global astronomy. It's a wake-up call on multiple fronts. First, it forces a reckoning with the fragility of our observational infrastructure. It will likely accelerate pushes for more distributed networks and formalize coordination through frameworks similar to the International Asteroid Warning Network. Major observatories will likely re-evaluate how target of opportunity time is allocated to ensure that high-priority interstellar objects get immediate, coordinated follow-up. Second, it recalibrates the geopolitical landscape of space science, forcing Western institutions to forge new alliances and advocate for more resilient, internationally managed observatories. Finally, it shines a light on the changing nature of discovery itself. It's becoming less about a lone genius at an eyepiece and more about managing vast, complex, and sometimes fragile global systems of technology, data, and collaboration. The 3IATLAS event is a powerful case study in this new scientific reality. The story of 3IATLAS is a powerful reminder that the universe doesn't wait for anyone. A visitor from another star system is hurtling through our cosmic backyard, and for a critical moment, China's observatories were our only eyes. This event will reshape not just our understanding of this comet, but the future of how humanity watches the skies. What are your thoughts on this shift in the cosmos? Let us know in the comments below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the future of technology and space. Thank you for watching Simply Science.